This is your pre-lab video for the determination of the solubility product of group 2 hydroxides. The objective of this lab is to determine the KSP of 3 essentially insoluble hydroxides. And what I mean by KSP is K is simply an equilibrium constant, just like you've been calculating it in the past, but it's of the solubility of a solid ionic species. We will be titrating saturated solutions of these hydroxides with hydrochloric acid to determine the amount of hydroxide that is in solution. And we'll be using this to calculate the KSP. Once you have the KSP of several hydroxides, you will be determining whether or not you see any trends. So this is a solubility equilibrium. We've been talking about all types of equilibria, and in this case we're just talking about a solid dissolving into its ions. So now if a salt is considered insoluble, it's actually in equilibrium with its solid state and a small amount of hydrated ions. This equilibrium lies very far to the left toward the solid. So we're considering it insoluble because it's mostly still in the solid form, but we do still have some of these ions in solution. But the KSP will be much less than 1. For example, if we have magnesium hydroxide here, this is our equilibrium and this is our KSP. Now notice that we have products over reactants raised to the power of their coefficients. So we have magnesium ion and hydroxide ion raised to their coefficients, but we do not see the solid in this equation because it is a pure substance, it's a pure solid. We'll be using titration in this lab, and titration is used to determine concentrations of unknown solutions. An acid-base titration is one example of a type of titration in which we use a neutralization reaction. So we neutralize our hydrogen ions or our hydronium ions, our H3O+. We react those with hydroxide ions and produce water. In this experiment, you're going to titrate your solutions of your insoluble salts, right, your quote-unquote insoluble salts, with HCl. The 3 saturated solutions you'll be using are magnesium hydroxide, calcium hydroxide, and strontium hydroxide. The net ionic equation for the reaction between all of these hydroxides and HCl is this. So we have hydronium ion, really H3O+, but I've simplified it here. It's just H+, plus OH goes to H2O. Equivalence point. The equivalence point of a titration occurs when the number of moles of titrant is what you're adding to your sample, so it's what is in the burette. Okay, so this equivalence point occurs when the number of moles of that titrant, in our case it's HCl, is added is exactly the same as the number of moles of the analyte. That's the sample, that's what you're adding the titrant to. In this case it's the OH ions from the dissolved solid, the dissolved hydroxide in the sample. We recognize the equivalence point by a change in color of an indicator. We're using phenolphthalein in this experiment and it's pink in basic solution. Now our sample is basic. We have our hydroxide in our sample. Our hydroxide is our sample, and pink is the color that phenolphthalein is in basic solution. So it's going to start out pink and you'll be adding acid. Once the equivalence point is reached, then you will have that color change from pink to colorless. The volume of the acid added can be measured using the burette that we're dispensing it with, and it will determine the concentration of the base that's contained within it, because we know that once we reach the equivalence point, we've reached the point where the moles of the acid equal the moles of the hydroxide. So our procedure. You'll be pipetting solutions of saturated hydroxides into an Erlenmeyer flask. It's really important that you do not get any solids into your Erlenmeyer flask because those solids will dissolve as the acid is added and it will give you an error for the amount of hydroxide that was actually dissolved. Once you have your sample in your Erlenmeyer flask, there's a few samples that you do have to add water to as well. You want to use purified water. You'll add your indicator. Don't forget to add your indicator or else you'll see no color change. And you will titrate with HCl. That means your titrant, your acid, is in the burette. You need to record the molarity of the acid in your notebook. You also need to record the initial volume and the final volume of the burette. And recall that you will measure the volume according to the bottom of the meniscus, and you need to record 2 decimal places for each volume that you measure. So in this case, you can see how the burette is, the graduation markings here are upside down because we are dispensing. So here's 20, 21, and 22. So in this case, we can read this. This starts out at 20. It's more than 20, but less than 21. And then you can measure quite easily these graduations. There's 5, 6, 7, 8, 9, and that would be the 21 mark. So this is 21.9, but you can see that you can estimate that this meniscus is between the 20.9 and the 21. So I would read this as 20.9, say 6. 20.96. So you would record to 2 decimal places for your burette. So just kind of a recap of things to keep in mind. You want to make sure you don't have any solid drawn up in your pipette and into your sample. You don't want to start your burette at 0. It's bad form, it's bad laboratory form. You don't need to make sure that your burette starts exactly at 0. Get it up close to the 0 mark, somewhere between, say, 5 and 0, and just read it. And record that as your initial volume. Make sure you record your burette to 2 decimal places. That means you have to estimate that last decimal place. Make sure you don't forget to add indicator, because you'll never see a color change. It's a good idea to put a piece of white paper underneath your flask, so bring one of these to lab so that you can see the color change easier. There's a method that you can add half a drop from your burette. If you let your burette just out a little bit and you will have a hanging drop there that doesn't quite go down, you can rinse the tip of the burette with purified water with your squirt bottle and rinse half a drop so that you can get very, very small amounts. You can add very small amounts to get to your end point. And you want to stop when you reach the end point, which is indicated by the color change. It's starting out as pink and it will go to colorless. And you can get the titration end point to be just this very, very pale pink. So you want it to be like just colorless, or the pale, pale pink in between pink and colorless. That's your end point. That's when you will measure your final burette reading. So you read your burette from the start. That's your initial burette reading. You dispense until that pink color is just pale, pale pink or just turned colorless, and you record your final reading. That is your volume of acid added, so that the moles of acid added equal the moles of hydroxide that were dissolved in your solution. You'll do 2 trials for each of the 3 hydroxides that will be provided for you, and you'll average those 2 trials. You have to calculate out the KSP for both individually and then average them. So calculations. So this is your reaction, remember. We have the proton, or the hydrogen ion, plus the hydroxide goes to water. So you will have the molarity of your acid. You need to record that. That will be provided for you. The liters of HCl added. This is off your burette. So you subtract final minus initial volume. That'll be in milliliters. You need to turn that into liters. If you multiply that by the molarity, that will give you the moles of hydrogen ion that you added to your sample. The moles of hydrogen ion equal the moles of hydroxide ion with this balanced equation when you are at the end point. So once you reach the end point, which is when you'll be recording the data, you'll have equal moles of hydrogen and hydroxide. If you divide your moles of hydroxide by your liters of sample is the amount that you pipetted from the original stock solution. So if you pipetted 1 milliliter, you turn that into liters. Now you have moles divided by liters gives you a molarity of hydroxide ion. This is one of the terms in your KSP equation. You will use the molarity of your hydroxide ion to determine the molarity of whatever metal ion you have for that particular hydroxide. So in this case, magnesium hydroxide, you want to write out your balanced equation for the dissolution of magnesium hydroxide into its ions, and you can see that there's a 2-to-1 ratio here of hydroxide ions to magnesium ions. So you can do a mole-mole ratio and change hydroxide ion concentration into whatever metal ion you're talking about. You'll have 3 different kinds. Once you have your hydroxide ion concentration and your metal ion concentration, you can put it into this KSP formula and solve. Safety. Your strontium solutions must be retained and collected in the hood as directed by your laboratory instructor. Make sure you wash your hands often. It's always a good idea. But also, if you get any of the solutions on your hands or on your skin at all, make sure you wash it off quickly. Don't pour any solutions over your head. It sounds like I don't want you to pour it onto your head. I don't want you to do that either. But I'm talking about the level up above your head or above your eyes. The burettes in the clamps are set up such that the top of the burette will be over your head, and you have to refill after every single titration. So you will be doing 6 titrations. After every single trial, you have to refill the burette. That's very important. And when you refill the burette, I want you to take the burette off the clamp and bring it down to, say, your waist level or somewhere comfortable so that you're not looking up over and pouring acid up over above your eye level. So bring it down and pour it carefully. Make sure you don't go past the 0 mark because you need to be able to read it. And that concludes your pre-lab video.